Hello and welcome to video lesson 19 on Mohr's Circle. Our learning objectives are to summarize the positive convention for stress elements that we will use for drawing Mohr's Circle and how that differs from the normal positive stress convention for stress elements in plane stress or plane strain. We want to be able to draw Mohr's circle for stress transformation. And then we want to be able to use it to calculate stresses on rotated elements using the diameter and rotation of the diameter. We'll also be able to calculate all of the important principal stresses, principal directions, max shear stress, everything that we learned how to do in the last lesson with Mohr's Circle. So read section 7.2 in Beer and Johnston. Let's talk about the positive sign convention for using Mohr's Circle. This is different from the positive sign convention for a stress element. You'll notice that, like the positive sign convention on stress elements, these sigmas are all positive in the tensile sense. However, taus are only positive when they spin the element in a clockwise fashion. So what that means is, by necessity, one element will be a positive element and the other element will be a negative element for shear stress. So we would always have sigma x and negative tau xy and sigma y and positive tau xy. So if we had an element that was in a positive sense, where all of the stresses on the original tensor element were positive, we would have a negative sigma, a negative shear stress on the x face. Tau xy would be negative on the x face, and tau yx would be positive on the y face. So this is only for purposes of constructing Mohr's circle. Otherwise, we would have we would have our normal sign convention where these are both positive when they point at the upper right corner and the lower left corner. So to construct Mohr's circle, we would take any 2D stress element and we would take this element that's in its positive sign convention, and what we would do is we would come up with 2 points that are going to define the diameter. We're going to use sigma x and negative tau xy. This would be negative because for it to be positive, it would have to go downward, but it's going upward. So we have sigma x and negative tau xy, and it would be, for instance, that point right there. And then what I would need to do is I would need to draw the other point as sigma y and tau yx, which is the same magnitude as tau xy. But for this surface, that's going to end up being a positive number because the stress on the y face is spinning clockwise. So I would find this point right here. Now, if I wanted to find the stresses on an element that had been rotated by an angle theta, I could use Mohr's circle to do this by rotating the diameter of Mohr's circle by 2 theta. Now, you might remember this 2 theta before from lesson 17, where we had some very interesting observations that as we changed the angle of inclination of the plane that we were interested in by theta, we would be able to find the point on a circle if we moved the diameter by 2 theta. So we've seen this before, and this is a result of both the change in force component or traction component that's acting on a plane of interest, and a result of the change in area of the plane of interest. So we end up with the same 2 theta kind of rotation for every theta we would rotate our element on Mohr's circle. So if we want to find the stresses on a new element at the same point in a new rotation, we would just rotate the diameter of Mohr's circle 2 theta in the same direction that we rotated the element. And that's how we would construct Mohr's circle. So how would we use Mohr's circle? Well, there are 3 important ways we can use it. First of all, as we talked about just a minute ago, just now, if we wish to find the stress on an element rotated by theta, all we need to do is rotate the diameter of Mohr's circle by 2 theta in the same direction. Second of all, we might want to know max in-plane shear stress. That's a very important quantity in determining whether a material is likely to yield or not. And that would be given to us by the radius of Mohr's circle, and that radius is equal to the square root of sigma x minus sigma y over 2 quantity squared plus tau xy quantity squared. Third of all, we might want to be able to get to the principal angles and principal stresses. So the principal stresses would be sigma average, that quantity that we're going to call sigma average. It's where sigma x and sigma y, the line containing those 2 points, crosses the sigma axis. And that would end up being sigma x plus sigma y over 2, because that's going to be the midpoint of the diameter. So we call that point sigma average, and that's the center of Mohr's circle. So the principal stresses are going to be equal to sigma average plus r and sigma average minus r. So the principal angle would be half of the angle that we have to rotate the diameter to make it lie on the sigma axis. So that's 3 ways that we can use Mohr's circle. So let's consider an example now. So for our example, we want to figure out, first of all, what the stresses are on the rotated element shown here, where the angle of rotation is 30 degrees counterclockwise. And I've got original stresses of negative 24 ksi for sigma x, negative 6 ksi for tau xy. Why a negative 6? Because these 2 arrows are coming together at the bottom right-hand corner and top left-hand corner. And then I want to find all of the quantities I would have wanted in the last lesson: sigma p1, sigma p2, tau max in plane, and theta p and theta s, the principal angles and the shear angles. So first of all, let's take a look at the stress on a rotated element. So I'll keep the original element close by, and we'll take a look at Mohr's circle on a new sheet over here. So first of all, I would know that tau, so sigma x and negative tau xy would be the thing that I would want, but however, I'm going to go with negative 24 and positive 6 as the first point, as the sigma, as the x base point. Why? Because the 6 ksi magnitude stress is spinning the element clockwise. So that would be a positive shear stress. So I'm going to locate the point negative 24, 6. Then on the y face, I've got 0 for the sigma, and I've got negative 6 because the shear stress on the y face wants to spin the element counterclockwise. So that would be a negative 6 here for the shear stress. So I've got sigma y and tau xy as 0 and negative 6. So -6 is actually the value of tau xy. So whatever the tau coordinate of this point is, whenever we rotate, our diameter is also going to be the value of tau xy for whatever element we end up with. So we've got the 2 points that we need to draw the diameter of Mohr's circle. And we now have what we need to get sigma average, and sigma average is -12, right there. So if I'm interested in finding the radius, which I should be, the radius is going to be determined using this right triangle, and the radius would be the square root of 12 squared plus 6 squared, and that would be 13.4. And the angle that this diameter makes with the sigma axis would be arctangent of 6/12, or 13.28 degrees. So this angle is 13.28 degrees, and this angle is also 13.28 degrees. So I can also identify the location of these other endpoints, which is what I really want for the stresses on the rotated element. So I want to rotate my element clockwise by 30 degrees, which means the diameter of Mohr's circle has to rotate. Sorry, I want to rotate my element counterclockwise by 30 degrees, so I have to rotate Mohr's circle by 60 degrees, the diameter by 60 degrees. So this angle is 13.28 degrees. This angle is 46.72 degrees. And now I can use right triangle trigonometry to find at this point sigma y and tau xy, and I can use right triangle trigonometry to find the coordinates of sigma x prime as well. So when I do that, I find that sigma y prime is equal to -12 plus 13.4 cosine of 46.72 degrees, and that gives me -2.81 KSI for sigma y prime. Sigma x prime would be -12 minus 13.4 times cosine of 46.72 degrees, and 21, and that would be 21.19 KSI. And then for tau xy, I just need the y coordinate of this point here for the shear stress in the prime system. That's going to be a positive number. It's going to be equal to 13.4 sine 46.72 degrees, or 9.75 KSI. So if we take a look at our stress element, our original element looked like this. The stress on the x-face was -24, it was compressive. The shear stress was -6 because it was pointing at the bottom right hand and the top left hand corner. Now, when we consider the element that's been rotated by 30 degrees, sigma x is still compressive. Sigma x prime is -21.2. However, tau xy prime has changed in magnitude. It's now 9.75 KSI. And we have picked up a compressive stress on the y face of -2.81 KSI. So that would be the stresses on the rotated element. Now, if I wanted to find all of the principal things that we learned how to find in the last lesson, I would know that the principal stress, sigma P1, would be given to me by the average stress plus the radius of Mohrs Circle, and that would be -12 plus 13.4. That would be 1.4 KSI. Sigma P2 would be given to me by the average stress minus the radius. So that would be -12 minus 13.4, or -25.4 KSI. The maximum shear stress is also equal to the magnitude of the radius, so that is 13.4 KSI. And I want to say a word about principal orientations. A principal orientation can be found when you rotate the element by 1/2 of this angle. So this angle is what we're going to call 2 theta p. And most of the time, problems in the Beer and Johnston textbook are going to just ask you for the smallest angle, theta p, that will rotate you into a principal orientation. And if we do that, that is 13.28 degrees, and we would be rotating counterclockwise. So if Beer and Johnston were asking for the angle here, it is very likely they would ask you for, they would want that number. However, I do want to note that we can add 90 degrees or take away 90 degrees from that number, or any multiple of 90-degree angles we want. And it would just be swapping we would switch the subscripts for X and Y. So this would be a 13.28 degree rotation. This would be a 103.28 degree rotation. So you can see that if I did another 90-degree rotation on this, I would swap the X and Y subscripts, and I would end up with a face where the sigma axis is the most positive. And that's the orientation that we drew in lesson 18. So I just wanted to make a brief note of that to close the loop with lesson 18. So the planes of maximum shear stress occur at 13.28 plus 45 degrees plus or minus 90 degrees. And that would be 58.28 degrees plus or minus 90 degrees. So you can see here, this would be 13.28 degrees. And this would be a 45-degree angle more, and this would be the plane on which the maximum shear acts. That's all for lesson 19 on Mohrs Circle.